This question is about iron and its ions. Discuss the role of iron as a heterogeneous catalyst in the Haber process. You should include the meaning of the term heterogeneous catalyst, how iron acts as a heterogeneous catalyst, and the factors that affect the efficiency and lifetime of the catalyst. So we can tell from the structure of this question it's probably the level of response. There are 3 bullet points, so they'll probably relate to the 3 stages, so make sure to answer something in all 3 parts to ensure that you're covering all 3 stages. So I'm going to start in order. The meaning of the term heterogeneous catalysis. So hetero meaning different. So a heterogeneous catalyst is a catalyst in a different, so there's the hetero part, state or phase to the reactants. So in this process, the reactants are gases and iron is a solid. So that's what heterogeneous means. What does catalyst mean? So a catalyst is a substance or species which speeds up a reaction without being used up. Don't say used on its own, used up, or it is unchanged. It is used, but then it's reformed. It does this by providing an alternate route of lower activation energy. So how does iron act as a heterogeneous catalyst? This is normally a 3-mark answer in the main part of the paper. So the idea is that the reactants adsorb, so that means stick to, adsorb, so that's with a D, onto the surface of the catalyst. This adsorption weakens bonds and then they break. So it lowers the activation energy because it lowers the minimum energy required to start the reaction by breaking the bonds. New bonds form, so that's the products, and the products desorb, leave, from the catalyst surface. And then our 3rd bullet point was the factors that affect the efficiency and lifetime of the catalyst. So the factors that affect its efficiency are its surface area. So we often use a sort of a support and then a thin layer on a support. That way we can get a lot more iron surface area but for less cost. So a thin layer of metal is placed on a support to increase the surface area whilst reducing cost of expensive metal. So that's how we could improve its efficiency. And then it asked us about its lifetime. So we need to say that catalysts can be poisoned by impurities which bind to and block active sites. Therefore, reactants should be purified before use. Okay, the next part of the question says Fe2 plus ions catalyse reaction between peroxidized ions and iodide ions. Explain why this reaction is slow before the catalyst is added, and give 2 equations to show how Fe2 plus catalyses this reaction. Okay, so we know that this reaction is slow before we add a catalyst because negative ions repel, giving a very high activation energy. What we need to do now is write the equations. Now, you might have memorised these. If you haven't memorised these, it's worth thinking about how you could work them out. We know in this reaction, S2O8 2- is going to SO4 2-. It says that there's 2 of those. If we look at that, the atoms balance, but the charges don't. So we know that this has got to have 2 electrons on the left. So that is a reduction, which means that the 2 iodide ions going to iodine plus 2 electrons must be the oxidation. And we know what's happening with the Fe2 plus is the Fe2 plus is moving through its variable oxidation states. So this is going, Fe2 plus goes to Fe3 plus an electron. This would be oxidation, and then Fe3 plus can go back to Fe2 plus by reduction. So if we were trying to use this information to come up with the 2 equations, we can see that if we combine the top 2, obviously doubling the Fe one so that we have 2 electrons in each, and we're going to do that on the bottom one as well, and then we combine the bottom 2, we will have 2 sets of equations starting with Fe2 plus and ending back with Fe2 plus. So I'm going to combine the top 2. So I'm going to have 2 Fe2 plus S2O8 2- goes to 2 Fe3 plus 2 SO4 2-. And then I'm going to combine the bottom 2. 2 Fe3 plus 2I- goes to 2 Fe2 plus I2. Give a reason why Zn2 plus do not catalyse this reaction. Zn2 plus is the only ion of zinc. You just have to remember that. Remember that zinc only exists as zinc and Zn2 plus. It doesn't have multiple different oxidation states other than the metal and the 2 plus ion. And then we've got a calculation part to the question. Iron reacts with dilute hydrochloric acid to form iron 2 chloride and hydrogen. A 0.998 sample. So we've got 0.998 grams of iron. And then we've got 30 centimetres cubed of 1 molar hydrochloric acid. It says one of these is in excess and the other limits the amount of hydrogen produced. Calculate the maximum volume of hydrogen produced. Give your answer to 3 significant figures, and we want it in metres cubed and we want it to 3 significant figures. So I'm just going to go down at the bottom and write 3 significant figures under the answer line so I don't forget. Metres cubed is the units for PV equals nRT, so that's going to be fine. So the first thing I need to do is work out who is in excess. So the number of moles of Fe, 0.998 divided by 55.8 on your calculator. And then I'm going to do the number of moles of HCl. So 30 centimetres cubed into decimetres cubed. 0.03 moles. So 0.0179 moles of Fe needs, you would need to, on your calculator, double it. 0.0358, because the ratio is 1 to 2, you would need to double it. So it needs 0.0358 moles of HCl, and you don't have 0.0358 moles of HCl. So HCl is the limiting reagent. We haven't got enough HCl to use all the iron. What that means is that the moles of H2 hydrogen produced will be, and it's because it's a PV equals nRT and we want to do the volume of hydrogen, we need to link the moles of the limiting reagent to the moles of the gas. So the number of moles of hydrogen equals the number of moles of HCl over 2, because it's a 2 to 1 ratio. So that would be 0.03 divided by 2, 0.015. And then if PV equals nRT, V equals nRT over P. So 0.015 times 8.31 times the temperature. So 30 degrees C is 303 Kelvin. And then we want to divide by the pressure, which was 100 kilopascals, but we need it in pascals, remember, so times 10 to the 3. Put all that in our calculator and we'll get 3.78 times 10 to the minus 4 to 3 significant figures. And that is already in meters cubed. If we wanted that, had wanted that in centimetres cubed, it would have been 378. Some reactions of ions in aqueous solution is shown in figure 2. Identify A and its colour. So this is Fe2. So this solution here is green, and this solution here is kind of an orangey brown. If we add carbonate ions to a 2+, then we just get the metal carbonate, which would be FeCO3, and its colour would be a green precipitate. It did only ask for its colour because it has told us it's a precipitate, so I didn't need to write precipitate. Whereas the 3+ are more acidic because they have a higher charge density, and so they react with the carbonate in an acid-base reaction, and they make the hydroxide precipitate. So the precipitate from ion 3 would be where you have 3 waters and 3 hydroxides. And that would be a brown precipitate. And the ionic equation, so the ion 3 hexaaqua ion is ionic. The carbonate ion is the part of sodium carbonate that we need, because this ion is a positive ion, so we need the negative ion, so carbonate. Since we've got 2 3+, we need 3 2-. And we're going to make our ion 3 hydroxide precipitate. And then 3+ are acting as an acid, more acidic, so we get carbon dioxide and water. And if we balance that, we need 3 of each of those. And the last part of the question says, explain why an aqueous solution containing Fe3+ has a lower pH, so is more acidic. So we'd say Fe3+ is smaller and more highly charged than Fe2+. Fe3+ has higher charge density. Therefore, Fe3+ is more able to polarize water more OH bonds weaken and break, so more H plus ions are released, and that is what makes it an acid.